All right, so let's start with chapter 1, temperature. So we're doing temperature in this chapter. We'll study about temperature. Okay, what we are doing is, so the first 4 chapters from the book, the first chapter is temperature and heat. The second chapter is kinetic theory of gases. The first law of thermodynamics. This is a conservation of energy principle that includes heat. And this is the second law of thermodynamics, which will introduce you to the idea of entropy. Okay? These 4 topics are part of a subject called thermodynamics, and you'll do an entire course in thermodynamics as engineers. Okay? So this is going to give you a little overview of the subject. Yep.
So is our last test, like, the last 4 chapters, is that our final report?
Right. Yeah. You have an exam every 4 chapters. So, yeah. There's no comprehensive final. Okay, so these 4 chapters will become a whole course in your junior or senior level, whatever, okay? Thermodynamics. So that's what, so let's study about temperature. Okay, this diagram shows you, let's say, a solid object. It could be this table, okay? And this end of the table is hotter than this end of the table. This end of the table is cold. Okay, and what this diagram is trying to show you is the following. Okay, so this is a solid object, and in a solid object, the atoms are in fixed location. You can come back 3 years from now, and that atom will still be there. Okay, but when this end is hotter, these guys vibrate with greater amplitude. When this end is colder, these guys are vibrating with a smaller amplitude. Temperature is a measure of average kinetic energy per atom. Okay? The hotter the substance is, greater the kinetic energy per particle. Okay? It's directly proportional to that. So for instance, the temperature in this room is 300 degree Kelvin, and the average kinetic energy per molecule corresponds to that. If you double the temperature to 600 degree Kelvin, the average kinetic energy will double. Okay, so that's what temperature measures. Okay, did you guys understand that? Okay, so let me show you a little app. And I'm going to quickly go over the slides. I'm just going to give you the punchline on each slide. You guys can read the stuff. You know. Okay, so here's the ideal gas, the pressure. This is an enormous pressure, 35 atmospheres, and it's at 300 degree Kelvin. Okay, 300 degree Kelvin is the temperature in this room. And this is a measure of the average kinetic energy per particle. Why do we say average kinetic energy per particle? Well, average kinetic energy. Yeah, so all of them are not moving at the same speed, and we'll talk about the distribution of speeds in a little bit, okay? Okay, now I'll warm the gas, and what will happen? So what I'll do is I'll warm it to 600 degree Kelvin, okay? Okay, so when you double the temperature, what you learn is you have double the average kinetic energy per particle. Okay? All right. So that's what temperature means, okay? So now we'll briefly go over. So thermodynamics, which is a subject which is a course you'll be taking, is a branch of natural science concerned with heat. Thermo meaning heat, dynamics meaning motion of heat. Okay, heat in relation to energy and work. Okay. So one of the questions you will ask is, let's say, okay, so for instance, in this problem, if this guy has 100 joules of potential energy, I can convert all of that to kinetic energy. Okay. So for instance, if you take your car on top of a mountain and it has 1,000 joules of potential energy and drop it, all of that can be converted to kinetic energy. One of the questions we'll be interested in is, let's say you burn gasoline inside your car, you release 1,000 joules of heat, how much of that can be converted to motion? You paid money for the gas, right? Not much, okay? Yep, so entropy will tell you how much of that can be converted into useful work, okay? So we'll be interested in answering questions like that, okay? Thermodynamics is, these laws apply to many particle systems, okay? So when you apply these laws, you can only apply these laws to a system which has many particles, Avogadro number of particles. Okay? So for instance, this room has about 1,000 moles of gas. Okay? You can apply it to that. You can't apply these laws to a system that has 100 particles, 1,000 particles. Okay? Interestingly, these laws apply in many areas: chemical reactions, transport phenomenon, black holes, cell biology, biomedical engineering, and even in economics. They've applied these laws, even in economics. Okay? All right. Now here's a very interesting fact. What is Avogadro's number, by the way?
6.32 times 10 to the 32nd.
10 to the 23. Okay? So roughly 10 to the 24. A trillion particles. Okay, and in this room there's about 10,000 moles of gas. So there's 10 to the 28 molecules in this room. Okay? And when we study the properties of this system, all we talk about is a handful of things. We'll talk about the temperature of the gas, the volume of the gas, pressure, energy, and so on. So we will characterize this system that is made out of 10,000 trillion particles by 5 parameters. Okay? And that's good enough for our business. Okay? So, I'm sorry? Yep. And these guys are called thermodynamic variables. Okay? And they're also macroscopic variables in the sense that you can use macroscopic tools to measure them. Okay? All right. Again, I'm going to go a little fast today. Okay? Yeah. So the zeroth law of thermodynamics says that systems in thermal equilibrium with each other have the same temperature. What do you think thermal equilibrium means? Yep.
Certain kinetic energies are the same.
Uh,
They're measured.
Okay, so here, let's do thermal equilibrium. Okay, so two objects are in thermal contact when they can exchange energy. Okay, and they are in thermal equilibrium when there is no net exchange of energy. Okay, no net exchange of heat. We'll talk about heat in a bit. Okay. So do you know any objects that are in thermal equilibrium? Every inanimate object in this room is in thermal equilibrium with each other. Every chair is in equilibrium with the floor, and so on. Are you in thermal equilibrium with your chair?
No.
No? Why not? I'm sorry?
We make heat.
Yes.
Chair takes that heat.
Okay, so the more technically correct way of saying is your temperature is higher than that of the chair. Okay? And so you're transferring net heat to the chair. If the chair's temperature was higher, then you would be gaining heat. Okay? So, for instance, oh no, it's not hot enough today, but probably you could go to Arizona and the temperature would be hotter than your body temperature. Okay? All right, so thermal equilibrium is there's always exchange of heat. The chair is exchanging heat with the floor and so on, but there's no net exchange of heat. Whatever it's giving, it's receiving back an equal amount. Okay. Okay. So the zeroth law says when they're in thermal equilibrium, they're at the same temperature. The first law of thermodynamics. Okay. So it took us a while to realize what heat was. Okay. Let me. Okay, so here's a model of a solid. Okay. In a solid, atoms are in fixed locations. Okay. What is preventing this guy from running away? I'm sorry?
Bonds.
Yeah. The forces between his neighbors are preventing him from running away. Okay? And the forces are large enough where you can come back 3 years from now and he'll still be there. Okay? These forces are modeled by these springs. Okay, now, at any given temperature, these guys are vibrating about their equilibrium position, so that's the kinetic energy. And the spring is expanded as well, that's the potential energy. Let's say I heat this solid, what will happen? I'm sorry? It's going to expand, so the springs will stretch. That means you've increased the potential energy. What else will happen? Yes, exactly. We saw that in the first slide. They'll oscillate with a greater amplitude. So when you heat the stuff, and they're oscillating in random directions, you're increasing the kinetic energy, you're increasing the potential energy, and all that. Okay, this internal kinetic and potential energy is the internal energy of the system. And when energy goes from here to a colder object, that internal energy is what's being transferred. Okay? So that's the internal energy that we were talking about over there. And that is heat. Okay, we didn't realize this 300 years ago. We thought heat was some kind of fluid in a solid. Okay, and eventually we realized that heat was the internal energy that is transferred from one object to another. And what determines that heat will be transferred from one object to another?
The specific heat capacity?
There's one number that will determine in which direction heat is transferred. Temperature. Yep. You're warmer than the chair and heat goes from you to the chair. Okay? You become colder than the chair, you'll gain heat from the chair. Okay? All right. So the first law of thermodynamics expresses the existence of a quantity called internal energy, okay, which now you know is random kinetic and potential energy of a system, and shows how it's related to distinction between energy transfer as work and energy transfer as heat. Okay, so let's understand this expression. Okay, so I'm going to do work on this guy. Okay, when I lift this guy up, I've done work on it. Okay, let's say So what was his potential energy now? 0. His potential energy now is 100 joules. His energy increased by 100 joules. Where did that energy come from? I'm sorry?
Applying work.
So when I did work on him, work is a mechanism of transferring energy from one object to another. Okay? So I transferred energy from me to him. Okay? Now, what am I doing here?
Are you transferring heat from yourself to him?
Very good. Okay, so that's what we're talking about. So uh, those are different processes. Distinction between energy transfer as work and energy transfer as heat. Okay? So, and then there is a second law of thermodynamics expresses the existence of a quantity called entropy. And one of the things about entropy is for an isolated system, the entropy never decreases. Okay. So we'll learn about that. And the third law of thermodynamics tells you that you can't cool a system to absolute zero. Okay? Absolute zero is 0 degree Kelvin. Okay. What you guys know about absolute zero? Mm-hmm.
Superconductors?
Mm-hmm.
What's the temperature when particles stop moving?
That's right. Okay. So here's how we realize this. Okay, so I'm going to cool this guy down. And as I cool it down, you see the molecules are getting slower and slower. And the best you can do is stop all the molecules. Okay? And that's when you reached absolute zero. You see, watch this. I'm going to cool it and watch the pressure. Why was the pressure decreasing?
The average kinetic energy of gas dropped.
Yeah, so they're not hitting the walls as hard, okay? And the pressure was decreasing. And when all the molecules stop, they're not hitting the walls anymore, and the pressure ought to go to 0. And that's how we discovered absolute 0, okay? So where's my graph for absolute? Oh, there it is. Okay. So that's how we discovered absolute 0. You took a flask like that. Let's say, hold up your flask. Hold up your flask. Okay, so you take a flask like that. In one flask, you put 2 moles. In another flask, you put 3 moles. Another flask, you put 5 moles. Okay. And in the 5 mole flask, the pressure is highest and so on. And then you start cooling the flasks. And what you find is the pressure goes to 0 at the same temperature. You get different amounts of gases. And that temperature is, of course, you can't go all the way because most gases would get liquids, become liquids. But so if you extrapolate, and the temperature at which the pressure goes to 0 is minus 273 degrees Celsius. Okay, and so we call this 0 degree Kelvin, and that's absolute 0. Okay, all right. Okay, so that's the third law of thermodynamics. Okay, so now you already know temperature is a measure of how hot an object is. Okay, and you will learn later in the next chapter that it's a measure of the average internal random kinetic energy per particle. Okay, so we'll give you the expression right now. So for an ideal gas, 3/2 kT equal to 1/2 mv squared. So what this expression is saying is, in this room, the average kinetic energy per molecule of the gas in this room is equal to 3/2 kT. Okay, so you'll see this expression in the next chapter. So you double the temperature, the average kinetic energy will double. Okay? So that's what that is. So by the way, our universe is 13.8 billion years old, and at the Big Bang, the temperature of the universe was 10 to the 39 degree Kelvin. So two objects are in thermal contact with each other if they can exchange heat with each other. All right, so what are you in thermal contact with?
Chair, air,
Mm-hmm. And,
Table,
I'm sorry?
pencil table in your clothes.
You're in thermal contact with everything. How are you in thermal contact with the wall?
the air.
You're also exchanging electromagnetic radiation. Okay? So you're in thermal contact with everything. This guy is in thermal contact with the table. Right now, the thermal contact is strong. I just weakened the thermal contact. Okay? So energy can be exchanged via conduction, convection, and radiation. Okay? Two objects are in thermal equilibrium if they do not exchange net heat energy. So when they're in thermal equilibrium, are they not exchanging any energy at all?
They are exchanging energy. The total is not changing.
That's right. Very good. So they are exchanging energy. He's giving him $5 and he's giving him back $5. Okay, so that's what's going on. So two bodies in thermal equilibrium have the same temperature. Okay, so the zeroth law essentially just says that if you're in thermal equilibrium, you're at the same temperature. So if A is in equilibrium with B and B is in equilibrium with C, then they're all at the same temperature. Okay? Hey, this is very interesting. So maybe one of you guys want to experience this. You want to experience this, Luke? Come on up here.
All right.
Touch the table. Touch this. Which is warmer?
Table.
Table is warmer?
Yeah.
Anybody else want to test it? They're at the exact same temperature. But you can feel it.
Yeah.
This will feel colder. We are bad thermometers. What we are more sensitive to is rate of heat loss. And that makes sense. You don't want to lose energy fast. You're losing, this is conducting away heat much faster than this. Okay? And that's what we're sensitive to, and so that feels cold. No. All right, so humans are to a large degree sensitive to energy fluxes rather than temperatures. Okay, so which you can verify yourself on a cold, dark morning in the outhouse of a mountain cabin, equipped with wooden and metal toilet seats. Both seats are at the same temperature. Yeah. But your backside, which is not a very good thermometer, is very effective in telling you which is which. Okay, so we know that temperature measures the average kinetic energy per particle, and so now we want to have a scale to measure temperatures in. Okay, so here are three commonly used scales. Okay. To make a temperature scale, what you need is two physical phenomena that happen at the same temperature. Okay. So here are two commonly used for everyday temperatures. For other research temperatures and stuff like that, they use other phenomena, but okay, for everyday use, what this is, ice point is at atmospheric pressure, 1 atmospheric pressure. You can melt ice in the morning, you can melt ice at night. 3 years from now, and if you stick your finger in there, it'll feel the same temperature. Again, you have to do this at 1 atmosphere. You can boil water at 1 atmosphere. You can do it today, tomorrow, yesterday, any time of the day. It'll feel the same temperature. Okay. Now, if you boil water at 2 atmospheres, it'll feel hotter. Okay. So you have to maintain 1 atmosphere pressure. Okay, so here are two physical phenomena that happen at the same temperature under defined conditions. Okay. And now to make a scale, you can make any scale you want. You can call this anything you want, and that anything you want. If you want a finer scale, you'd call this 0 degrees, and you would call this 1,000 degrees. Yeah. Anyway, these Celsius guys call this 0 degrees Celsius, 100 degrees Celsius. These guys call this 32 degree Fahrenheit, 212 degree Fahrenheit. See, between these two temperatures, there's 180 degrees. So this is a finer scale than this. The Kelvin guys call this 273 and 373. Okay, so here's a question for you guys. There's 100 degrees between these guys, these two, and 100 degrees between this. So sounds like this is a redundant scale. Why did we have the Kelvin scale? Yep.
It's more scientific because 0 Kelvin measures absolute 0. So it's better to have that 0 point, and then it goes up by the same amount because they wanted to keep it close to Celsius.
Yep. So we had the Celsius scale, and then we learned that the coldest temperature, we did that experiment a minute ago, the coldest temperature was minus 273 degrees Celsius. Try explaining that to your little brother. The coldest temperature is minus 273 degrees. Why minus 273? It's not aesthetically pleasing, so we just call it 0 degree, and that's all. It's just moving the origins. So this scale is the exact same as that, with the origin at a different location. All right, so the size of the degree is the same. So now, how many temperature scales can you make? Infinite number. Okay. All you need is two physical phenomena and call them anything you want. Yeah. So, for technical reasons, we use a more precise phenomenon. Absolute 0 is one unique definition, and a triple point of water is a more precise temperature. Okay? And the triple point of water happens at 273.16 Kelvin. Okay? Do you guys know what the triple point of water is? Anybody know what the triple? Yeah.
It's when it's boiling, liquid, and frozen at the same time. Or sorry.
You're barking up the right tree when all three phases coexist. Okay? So we'll, and here's a picture. So here is liquid water, here is water vapor, and there's solid water. And this graph tells you, so this is a phase diagram for H2O. So let's understand phase diagrams. This is a very important thing. What is a phase diagram?
Shows
Yeah.
the phase of matter given a certain temperature and pressure.
Right. Very good. So the phase diagram, see, this is, there are any, you can plot them, use any thermodynamic variable. So this is plotted with pressure and temperature. So, and this is, the phase diagram is for this substance. Okay? And what this diagram is saying is, at this temperature and this pressure, this substance can exist only in vapor phase. So this is a pretty, this diagram contains a lot of information. Okay? At this temperature and this pressure, what is it saying?
Exists in solid form.
It can only exist in solid form. If you have water, it's in solid. Okay? You can't have water vapor. You can't have liquid water at that temperature and pressure. On this line, what it's saying is solid and liquid can coexist. Okay. So at 1 atmosphere and 0 degrees Celsius, ice and water can coexist. So you go to a restaurant next time, you see a glass of ice water, you don't need a thermometer. You know its temperature. What is its temperature? 0 degrees Celsius. Yep. All right, so this phase diagram gives you a lot of information. Okay. Here is the triple point. So along this line, solid and liquid can coexist. Along this line, liquid and vapor can coexist. Along this line, solid and vapor can coexist. Okay. So see, below this, and this is partial vapor pressure, below this pressure, you can't have liquid water. Okay? You either have solid or water vapor. So there's triple point. And the neat thing about triple point is you increase the pressure and the temperature, you can turn it all into water. Decrease the pressure and increase the temperature, you can turn it all into gas. Decrease the temperature, you can turn it all into solid. Okay, so you can fall in any direction. Now, here's an interesting thing about this phase diagram. So for most phases, so you have phase diagram. For what kind of stuff do you have phase diagrams? For pure substances, any pure substance, okay? For most substances, this solid-liquid interface, this slope is a positive slope. It's like that. And by the way, this diagram is not to scale. See, this is, they draw it like that to illustrate various points. Okay. So for most substances, the line is like this. For water, the slope is negative. And here's an interesting application of this fact. All right, you guys have skied before, I take it, or at least you know about skiing. And what is going on there? Why is skiing possible?
The pressure,
Mm-hmm.
the pressure of the skis actually melts the ice and
Yep.
creates liquid water from the ski.
Exactly, very good. So let's say there's snow on the ground and the snow is at minus 5 degrees Celsius. Okay. And you step on the ski. What you've done is you've increased the pressure and you melted the snow under your feet. And that that's your lubrication. Okay. So skiing is possible because of this negative slope. Had the slope been positive, you gotta get on skis and you just make the ice, you pack the ice. It wouldn't melt. Okay. Anyway, these phase diagrams are very useful, and you will learn about them. Okay, so those are the temperature scales. All right, so triple point of water, we learned about that. Okay, these two formulas, what they do is, if you have a temperature on the Celsius scale, this tells you how to convert it to Fahrenheit scale. If you have, this one tells you, if you have a temperature in the Celsius scale, how to go to Kelvin scale. Just add 273 to it. Okay. So between these two equations, you can convert from any scale to, from one to the other two scales. Okay. Okay. So here are some temperatures we measured. Yeah. So, by the way, the temperature at the interior of the sun, in the interior of the sun, is about 15.6 million degree Kelvins. Okay. In the interior of the Earth, it's about 6,000 degree Kelvin, something like that. You'll have to look it up, Google it. And funnily enough, we know this temperature more accurately than this temperature. Okay, I can tell you about that. Okay. Look at this. You explode a hydrogen bomb, the temperature is 100 million degree Kelvin. So here's a bomb that has exploded, and there the temperature is 100 million degree Kelvin. All right. How did they measure that temperature? Did somebody stick their fingers in there? I'm sorry?
They're probably using kinetic energy at the interior of the plastic particles.
All right. So here's how. So the reason I bring it up is now we'll see how temperatures are measured. If you don't want to stick your fingers into something and you want to measure the temperatures, here's how you do it. All objects emit electromagnetic radiation. Okay? So we're talking about solids and liquids and real hot stuff. But anyway. Okay, so here's this just tells you, this is the intensity, tells you how much energy is coming per second per meter square. Okay, so there's the bulb. I can measure how much energy is passing per meter square per second. Okay, that's what this thing is. And this is the wavelength, that's the color of the light. Okay. So here's the sun emitting it, and that's the temperature of the sun, the surface temperature of the sun. Now let's say I'm going to change the temperature of the object emitting it. It could be this table, it could be the wall, anything you want. Okay, I'm going to change the temperature. What happened to the graph? I'm sorry? Every time the temperature changed, the graph changed. The graph was unique to a temperature. For every temperature, the graph was unique. So you want to measure the temperature of the wall and you don't want to touch it, all you do is you have to have a sophisticated instrument. At this wavelength, measure the intensity. At this wavelength, measure the intensity. At this wavelength, measure the intensity. Draw the curve and you know the temperature. Yeah. So that's how we know the temperature, surface temperature of the sun. We measure intensities of radiation. That's how we know the temperature, surface temperature of all those stars that are so far away. That's how we know the temperature of a furnace without sticking our fingers in there. That's how we know the temperature of an exploding hydrogen bomb. Yeah. And that's how those thermometers that go to a doctor's office work nowadays. They just scan your forehead, they're not touching you. Yeah. All right, so here are some temperatures that we measured. Okay, see, our personal experience is very small window. Okay, so the highest temperature in Libya and lowest temperature in Antarctica. This is a relativistic heavy ion collision, and look at that. The temperature there is more than 1,000,000,000,000 degree Kelvin. 1,000 times strong, hotter than the center of the sun. And this is done in a lab. Okay? All right, guys, why don't you take a 2-minute break?